This video looks at the normal distribution. Now, unlike the binomial distribution, the normal distribution is associated with continuous random variables. So remembering binomial is discrete, normal is continuous. Now, there is a formula for the normal distribution, which is here, but you don't need to remember that. Now, characteristics, what's the same for a normal distribution? It's always a bell shape. So as you can see on this side here, looking at the graphs, they're all bell-shaped curves. They're symmetrical. So they're symmetrical about the mean, median, and mode, which is in the middle of the distribution. The area under each curve is 1 square unit. So no matter which bell-shaped curve you look at or normal distribution, the area under the curve is 1 square unit. The mean, median, and mode are all represented by the highest point on the curve. Now, differences, the centre of each. For normal distributions, we use the mean as a measure of central tendency, but where the mean is depends on the normal distribution, unless we're looking at the standard normal distribution. The spread, which we measure using the standard deviation, is also different. So as you can look at these graphs on the right here, the mean for the green graph is higher than the mean for the red, but the mean for the red and blue graphs are the same. Now, the standard deviation, the wider the normal distribution, the greater the standard deviation. So it looks like the red graph probably has a greater standard deviation or similar to the green, and then the blue has a smaller standard deviation. Now, any normal distribution can be fully described by its mean and standard deviation. So as long as we know those two bits of information, we can work with our normal distribution. So in a normal distribution, we know certain things about it, and that's why we can work with it. So 68% of the values lie within one standard deviation. So this is +1 -1. So I know that 68% of values are between these 2 points. Okay, within 2 standard deviations, so from here to here, I have 95% of values, and then within 3 standard deviations, so all the way across here, I have 99% of my values. Okay. So looking at these questions here, what is the probability that a randomly selected normally distributed value lies between 1 standard deviation below and 1 standard deviation above the mean? That was, from the previous slide, 68%. The mean and the value 1 standard deviation above the mean, well, because it's symmetrical, okay, so this is my bell-shaped curve. If I know 68% are within 1 standard deviation above and below the mean, and it's symmetrical, then one side has to be 34%. So 68% divided by 2 gives 34%. Now the mean and the value 3 standard deviations above the mean. So when we were looking at our previous slide, -3 +3, this was 99%. So this is saying the mean and the value 3 standard deviations above the mean. We want to just know that. So it's going to be 99 divided by 2, which is going to be 45.5%. And actually, 49.5% would make more sense, wouldn't it? Okay. Now, standard normal distribution and Z-scores. If 2 distributions of scores are approximately normal and they have the same mean and standard deviation, then the raw scores from each could be directly compared. Now, because our means are different and our standard deviations are different, but they're both normally distributed, what we do is we convert our scores to what we call Z-scores. Okay, so we do what we call standardizing our distribution. It's kind of like when we convert values to percentages, so we can compare percentages. We compare our values to standard scores so we can compare them. Okay, so we're getting distributions with different means and standard deviations, turning them into standard distributions, which will have a mean of 0 and a standard deviation of 1. So let's look at an example. If a distribution of scores has a mean of 50 and a standard deviation of 10, then a raw score of 70, which is 20 scores or 2 standard deviations above the mean. Okay, so mean is 50, standard deviation of 10, so a raw score of 70 is the mean plus 20, and that 20 is 2 times our standard deviation. Okay, so that means we're 2 standard deviations above the mean. Now, that means that a score of 70 can be represented by a Z-score of plus 2, meaning it's 2 standard deviations above the mean. Now, finding the Z-score can be done using a formula, which is whatever our value is minus the mean divided by the standard deviation. So if we look at this example, we'd go 70 minus 50, which is 20. 20 divided by our standard deviation, which is 10, is 2. Okay, now a standard Z-score expresses raw score in terms of its distance from the mean. Okay, how many standard deviations are we away from the mean? Now, Z-score distributions have the same mean and standard deviation. The mean is always 0, and the standard deviation is always 1. And using our population values, mean is 0 and standard deviation is 1. Therefore, when scores from distributions with different means and standard deviations are converted to Z-scores, these scores can be directly compared because they have the same mean and the same standard deviation. Okay, a standard distribution has a mean of 0 and a standard deviation of 1. And the distribution of Z-scores is called the standard normal curve. The standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1, which I've already said. And the Z-score indicates the number of standard deviations the raw score deviates from the mean. And we use this formula here. Okay, you don't need to know the formula for the graph. Now remember that sign is really important. We need to know if we're above the mean or below the mean. So a positive Z-score means our score is greater than the mean. And a negative Z-score means our score is less than a mean. So if we have a positive Z-score, we're above the mean. If we have a negative Z-score, we're below the mean. So if we have a Z of -2, that's 2 standard deviations below the mean. If we have a Z-score of +3, that's 3 standard deviations above the mean. Okay, so in the normal distribution, the distance between the mean and a given Z-score corresponds to the proportion of the total area under the curve. So if we think back to that bell-shaped curve when I said that within 1 standard deviation, so -1 + 1, we had 68% of values between those two scores. So that's what we're relying on. Knowing how far we are from the mean can tell us what the probability is of having a score in that vicinity or in that region. And because we have this standard normal distribution, we have a table for them. So this table can be used for any standard distribution based on those percentages, like 68%, 1 standard deviation away from the mean, 99%, 3 standard deviations above the mean. So this table is looking at all those proportions. So if I look at a Z-score of -1.55, what I do is I go down to 1.5 on the left-hand side, and then I have to go across to 0.05. So that represents 1.55. The intersection of those two is 0.4394. So that means that if I think of my normal distribution, this is the mean. So a Z-score of 1.55 represents this proportion here of 43.94%. Okay, so my proportion is 0.4394 or 43.94%. Okay, in the next one, which is negative 0.93, I go down. Now, note it's symmetrical, so it doesn't matter if they're positive or negative. The table is all in positive. So you can see by this diagram here, it's always giving us a proportion between the mean and our Z-score. So the proportion for negative 0.93 would be exactly the same as a proportion for 0.93. So I go down the left-hand side to 0.9 and I go across to 0.03. So this proportion here represents negative 0.93. Okay, so this is 0.3238 or 32.38%. So I know that 32.38% of scores are between the mean and negative 0.93 standard deviations below the mean. That makes sense when we know that 68% of scores are between one standard deviation of the mean, half of 68, 34%. So we know 34% is between the mean and one standard deviation. So if we've got negative 0.93, that kind of makes sense, doesn't it? 34%, and this one's 32.38. Okay, now the next two are giving us the proportion. So what we need to do now is find those proportions within our table. So we're looking at our table for 0.3212. So we look within the middle, and we've got 0.3212 here. So the corresponding Z-score is 0.92. So Z equals 0.92. Okay, that could be plus or minus 0.92. Okay, it could be above or below. 21.9%, get a different color. Okay, 21.90 is right there. So that's corresponding to 0.58. So Z would equal plus or minus 0.58. So use your normal distribution table to try and answer these questions as I do. So this one says, using the normal distribution table, determine the value of the probability that Z is less than 2.3. So I strongly recommend drawing a picture. So there's your bell-shaped curve. 2.3 is over this side. It's positive. Okay? It wants what's the probability or what's the proportion less than 2.3. Okay? Now our normal distribution table will give us the value from here to here. So if we look up 2.3 on our normal distribution table, so looking here, 2.3, sec. So 2.3 is here. So that's 0.4893. 0.4893. Okay, but we need to add this side as well, and that represents 0.5 because we've got 50% to the left and 50% to the right. So this proportion here equals 0.5 plus 0.4893. Okay, so go to your calculators, or you should be able to work that out. It's 0.9893 or 98.93%. So you would expect 98.93% of scores to be 2.3 standard deviations or below. Next one, Probability Z is less than and equal to 1.327. Now the less than and equal to or the less than doesn't matter because it's a continuous distribution. We don't need to worry about that. So when we draw our diagram, we have our mean and 1.327, and we want this proportion here. Okay, so again, we're going to have to use our knowledge that from here to here is 0.5. We just need to read our table to find that there. So we go to our table and we look up 1.327. So 1.3 down the side, 1.327 is going to be between 1.32 and 1.33. Okay, so you could estimate halfway between there. So you might estimate it as being 0.407. Okay, so come back to here, and it's going to be 0.5 plus approximately 0.407. So I should put an approximate there. So that's approximately 0.907 or approximately 90.7%. Next, we're looking at greater than 0.5369. So draw a diagram. That one doesn't look great, doesn't look very symmetrical at all. Doesn't really matter though, I'm only trying to work out my answer from it. So 0.5369, and I want this area here. Okay, my normal distribution table is going to give me that area there. So once I find my proportion, I actually want to go 0.5 minus whatever the value is from the table. Okay, and that'll leave me that tail. So going to my normal distribution table, I'm looking for 0.5369. So 0.5369, 0.5, 0.5369. It's probably going to be closer to your 0.534. So you might want to approximate it as approximately 0.204 in between. So it's approximately 0.204. That's approximate. So 0.5 minus 0.204 is going to be approximately 0.296 or 29.6%. Okay, last one. We're looking at between negative 2.56 and 1.34. So we want all of this here. So we're going to find each one individually. One sec. So let's start with 1.34. Go to our normal distribution table. 1.34. I might use the pen so it looks different. 1.34 is 0.4099. .4099. Then we go back and look up 2.56. So 2.56 is there. So 0.4948. Is that there. So our proportion is going to equal 0.4948 plus 0.4099 because we want the whole distance between, and that is approximately 0.9047 or 90.47%. Okay, move on to our next one. Now we have an application problem. The height of male students is normally distributed with a mean of 170 centimetres and a standard deviation of 8 centimetres. Find the percentage of male students whose height is between 168 and 170 centimetres. So what we need to do is work out what our standard scores are. We're only using our normal distribution tables here, by the way. So our Z-score was x minus the mean over the standard deviation. So that's going to be my 162 minus the mean, which was 170. So mean was 170, standard deviation was 8, over my standard deviation of 8. So 162 minus 170, which would be negative 8, divided by 8, which is negative 1. And then my other Z-score is going to be equal to 170 minus 170 divided by 8, which is 0. Okay, so I'm finding the probability that 162 is less than my x, which is less than my 170, which I can now write that's the same as being between negative 1 and 0 in terms of my Z-score. So when we think of our normal distribution table, we're looking at that bit there. Now, if you remember that we've got 68% between one standard deviation above and below, you should realize that that's just going to be 68 divided by 2, which is 34%. And you don't even need to go to your normal distribution table for that. Okay, if we did go to our normal distribution table, we'd be looking up 1, which is 0.3413, which is approximately our 34%. Okay, the next one, between 170 and 186, we already know our Z-score for 170 is 0, so we need it for 186, so it's going to be 186 minus 170 divided by 8. So that's 16 divided by 8, which is 2. So the probability that 170 is less than my x, which is less than my 186, is the same as saying my probability that 0 is less than z, which is less than 2. Okay, so in terms of my diagram, I want to know between 0 and 2 standard deviations above the mean. Now, if you remember the 2 standard deviations above the mean, or that within 2 standard deviations of the mean, so plus or minus 2 is 95%. So that'd be 95 divided by 2, which would be your 47.5%. Or if you don't remember that, go to your normal distribution table, you look up 2, go across 0.4772. So 0.4772 from the normal distribution table, or 47.72%. Chances are, go to the normal distribution table, then you don't have to remember between 1 and 2 and 3 standard deviations. The last one, greater than 175, so my Z is 175 minus 170 divided by 8, so that's 5 divided by 8, going to my calculator, that ends up being 0.625, so my probability that my x-score is greater than 175 is the same as my probability that z is greater than 0.625. So thinking about my diagram, if I've got 0.625 here, I want that area there. So I'm going to go 0.5 minus whatever it is on my normal distribution table. So going to my normal distribution table, 0.625 is going to be halfway between the 2 and the 3, which is approximately 0.234. Okay, so we've got 0.5 minus 0.234 is, and it's approximately 0.266 or 26.6%. Okay, so use your distribution tables to do these, and then next lesson we'll look at how to use our calculators. Exercise is MathQuest, so on your Google Classroom. Questions 1 to 6 every second part, and question 8 to 10, again using your tables only.